Hi everybody! Today's team activity is going to be to draw some pictures to get a conceptual feel for what's going on in a half-life decay process. There are going to be 3 steps for you and your team to complete. The first one is to watch this introductory video that will work through an example for you and get you headed in the right direction. And then work with your team to fill in the pictures on these 2 sheets right here. You can either print this, there's a link available in today's folder on Schoology, or you can just draw your pictures on a separate sheet of paper. While your team is meeting to work on this, remember to take a picture of some evidence of your meeting so you have that to submit to your portfolio. When you've completed both pages of this as a team, one member of the team is going to log back into Schoology, and there'll be a Google form there. And while everybody's still in the meeting, that person's going to input some answers and as evidence that you've completed your work, and you'll put everybody's name on it as you push that form in. So what we can see here is that we have pictures that have a current sample, and then your job is to draw a picture of what would be left after 30 years. Let's look at an example here to get you started. I chose to draw for you the example of Krypton 85. If I want to draw what a sample of Krypton 85 will look like after 30 years, I really need to know 2 things about the Krypton 85. I need to know what type of radioactive decay it will undergo, so I know what its daughter nuclide will be, and I also need to know its half-life. Both of those pieces of information are available via Schoology under the half-life of the elements link. Just as a reminder, the half-life of the elements is the second link down on your page here. And you have to click there to actually leave Schoology. It brings you to a periodic table. I want to look up information about krypton, and I scroll down here to the bottom where we have the specific isotopes, and I want Krypton 85. And by clicking on decay modes, I can see both the half-life and its mode of decay. It's got a half-life, we'll just go with 10.7 years, and it's going to undergo beta decay. Coming back to my clipboard here, we've got a half-life of 10.7 years, and it's going to undergo beta decay. So I need to write an equation to describe this. We have 85, 36 krypton. Beta decay means that it emits a 0 minus 1 E. And then I have to figure out what my daughter is. 85 is 0 plus 85. 36 is negative 1 plus 37. And element 37 on the periodic table is going to be rubidium. So my daughter nuclide is an 8537 rubidium. Now I need to figure out how many kryptons and how many rubidiums are going to be left after 30 years. I'm going to create what's called a half-life T-chart. Time and amount remaining. Our time is going to be counted in years, and our amount remaining in nuclides. We start at time 0, and at this point, my picture has 8 of the krypton nuclides remaining. After 1 half-life, or 10.7 years, that amount's going to be cut in half. So I have 4. After a second half-life has gone by, or a total of 21.4 years, that amount gets cut in half again, and I'm down to 2 nuclides remaining of my krypton. And after another half-life goes by, I'll be down to only 1 of those remaining. So I'm supposed to draw a picture of my sample after 30 years. By best estimate, looking at my T-chart, 30 years is getting pretty darn close to 32 years, so it's probably reasonable to think that I probably only have 1 of those nuclides of my krypton remaining. So up here in my sample after 30 years, I'm going to have one of my kryptons left. But as we learned, in radioactive decay, you don't actually lose any nuclides. You have the same number of nuclides as what you start, you just change the identity of them. So in addition to the krypton that's left, for every one of the remaining 7 that underwent radioactive decay, you've got a rubidium in here. 85, 37, rubidium. I'm going to mark that with a rectangle just so that we can see very clearly that it's a different nuclide. And according to our decay equation, every time a krypton turns into a rubidium, a 0 minus 1e leaves the sample. So I have to do that 7 more times. Oh, oh, too many. I needed to stop before that. Got a little carried away here. Erase that guy. 1, 2, 3, 4, 5, 6, 7 radioactive particles, 7 leftover nuclides, and we've managed to draw a picture of what our sample would look like after 30 years. So now you and your team can go back to the half-life picture representations worksheet. You can start drawing your pictures. The first 4, you're allowed to assume that your daughter nuclide is stable. And then on the back is a little more complicated of a situation, radioactive decay of lead-210, which actually undergoes a 3-step decay process. Lead-210 is a radioactive isotope of lead. And so you're going to have to write the decay equations according to the process we've described right here, assigning each of the daughters in order a symbol. So the daughter of lead-210 is going to be the square, the daughter of that will be the triangle, and the daughter of that will be the star. Looking at the half-lives of these, you're going to decide how many you want in your sample afterward, and then draw a picture of what's going to be left after 22 years. When you're done, have one member of the team fill out that Google form, and then your meeting will be over.